I'm going to be talking about automatically generalizing proofs and statements. This work was done in collaboration with Anand, who you just heard from, and our supervisor, Tim Gowers. We've implemented a proof generalization algorithm in Lean. And what that means is we've developed an algorithm that takes in a formalized Lean math proof and outputs a more general theorem and proof. So this work builds on previous work by Olivier Pont, who implemented a precursor to this algorithm in the Rock programming language. Okay, so an example of this tactic in action. So suppose that we have a formalized proof that the square root of 17 is irrational. And suppose you prove this in the way you'd sort of expect, where you say square root of 17 is equal to A over B, where they're in lowest common, they don't share any common factors, and you ultimately get a contradiction. You would find that really the only fact you use about 17 in proving this theorem is that 17 is prime. And so this tactic will take in this formalized proof and generalize it to the theorem that for all primes, the square root of that prime is irrational. So just for a live demo of what's going on here. So here we have a proof. We've proven that the square root of 17 is irrational, and we've proven it in Lean, and we can click through and see there's nothing sort of suspicious going on here. It's a regular proof, sort of the way you'd expect to prove it. You write it in terms of A over B, and then you show 17 divides A and 17 divides B, and you end up with a contradiction. So now we can run our tactic called auto-generalize on this proof, and we say we want to generalize the 17 in the above theorem Erat square root. And we can see that the running of this tactic adds a new theorem to the context that says for any natural number that is prime, the square root of that number is irrational. And so just to show that there's no kernel errors and this is actually a valid proof, we can use assumption to close out this proof.
So I just want to point out that this algorithm doesn't derive the more general theorem that the square root of any non-perfect square is irrational if that reasoning step is not evident in the proof term. So we could modify this proof and add more machinery to it so it extends to this more general statement. But like modifying proofs significantly in order to get more general statements is outside the scope of this particular algorithm. We're focusing on what is the sort of low-hanging fruit of how far we can generalize a theorem as far as the proof allows. Okay, and so this is by no means the first proof generalization tool. Talia Ringer gives a really good survey of, along with colleagues, a really good survey of previous proof generalization tools, and some things I wanted to highlight were the precursor of this work in Rock by Olivier Pont. People have focused on generalizing inductive types specifically in Rock, and like Talia Ringer and colleagues. And Alex Best has created a program that generalizes type classes in Lean. So for example, if there's a proof that has the type class commutative group attached to it, but you really only need it, but the proof works for any group, then this program can generalize the type class in that theorem to just group. So our work is in this vein of proof generalization algorithms. Okay, so what do we add to what already exists? We focused on adding robust generalization of repeated constants and dependent constants. So I'll explain what I mean by that in these next few examples. So suppose you prove that the square root of 17 plus 17 is irrational. It would be very silly to generalize this to the theorem for all primes. The square root of the prime plus any prime is irrational. We should recognize that these are both 17, but they play different roles in the proof. And they can be generalized separately. And so our tactic can recognize that really this generalizes to the theorem that any prime, the square root of any prime plus any natural number is irrational. And so here we have that, the proof that square root of 17 plus 17 is irrational. And we run this tactic on it, and it generalizes like you'd expect to that the square root of n is irrational where n is prime, and or plus m where m is any natural number with no additional hypotheses on it. Another slightly more complex example of generalizing repeated uses of constant, we can consider the theorem that if you have a set A of size 3 and a set B of size 3, the number of functions that go from the first set to the second is 3 to the 3. And here we not only need to generalize some of these 3's to different things, but we also want to recognize that some of these 3's should be generalized to the same variable, that this first 3 is related to this 3 in the exponent here, and the 3 from the size of the second set is the same as the 3, the base of the exponent of this expression. So indeed, when we run this auto-generalized tactic, we see that we find that if we have a set of size n and a set of size m, then the number of functions that map from the first to the second has size m to the n. So we not only recognize when constants can be different, but also when they need to be the same for the proof to go through. Okay. Yeah, so that is just to make sure that that the generalization, that there are no errors in the proof. Yeah, so you don't need to write it, and it would work. I can show when this comes back on that I can remove that and the same code still works. But it's just a way to verify that the proof is correct, because then when I run assumption after creating the generalized statement, I can tell that it actually did prove that theorem, and it's not just something that looks like a statement of that theorem. Yeah. Actually, yeah, that'll be, yes, that is in the next bit where I talk about, so we generalize repeated constants and dependent constants. And so that would be a thing where we would be able to recognize that that 9 has a dependency on 3's. Oh, yeah, yes, yeah. The 27 has the dependencies on the 3's. And so if you asked this algorithm to generalize the 27, it should recognize that it also needs to generalize the 3's. Or if you generalize the 3's, it should recognize it also needs to generalize the 27. So that's, yeah, I'll talk about that in this next bit about generalizing dependent constants. Also, just to address your first question, so here we have the example and the theorem statement written, and I can, remove the theorem statement, and this function still runs. It still adds the more general theorem to the context. And
you can proceed now.
Yeah. Oh, yeah. That's okay. Thank you. Okay. So, yes. Okay. So, dependent constants. So, we could consider the example you gave, or also the example that the union of two sets of size 2 has size at most 4. You should not be able to just generalize the 4 without generalizing the 2, and you can't just generalize the 2 without generalizing the 4. So this algorithm recognizes, by looking at the proof, that the 4 is actually a 2 plus 2 and not a 2 times 2 or something else, and that the 2's need not be generalized to the same variable. and maybe I should emphasize here, like the way that we detect this is by looking at the proof. If we were just trying to generalize theorem statements and all we had was this statement, this algorithm wouldn't work. It's a proof generalizer, and then we can run type inference to figure out what the more general theorem is. But so by looking at the proof, we recognize that there's a dependency here, and so we can generalize to the theorem that the union of a set of size n and a set of size m has size at most m plus m, and we get that corresponding proof. So here we have this theorem for a set of size 2, 2, and maximum size 4 of the union. And here when we say we want to generalize the 2, then we get a set of size n and a set of size m has a union which has size at most n plus m. Another more complicated example, suppose that we want to prove that, or suppose that we already have the proof that a no 4 vertex graph has degree sequence 1, 3, 3, 3. So we're saying, and the way this proof works is we say, well, all but one of the vertices are connected to every single other vertex. Then we shouldn't have a vertex that's just a leaf. That would be impossible. And so say we've proven that. We can't have one vertex with degree 1 and all the rest have degree 3. Then we should be able to recognize there's a dependency here. If we generalize this 4, then this should generalize to, if we generalize the 4 to an n, we should generalize the 3 to an n minus 1. And so indeed, this tactic can recognize that that's what needs to happen, and that we can't have a graph where one vertex has degree 1 and all the rest have degree n minus 1. And it also recognizes that this proof only holds when n is greater than 2. So this only works for a 3, 4 vertex graph on. Any questions at this point? Okay. Okay, so now it makes sense to go into how this algorithm actually works. So we take in a proof to generalize and a constant to generalize in the proof. So that's here, for example, the proof to generalize is this one called impossible graph. The constant to generalize is 4. And first, we abstract all occurrences of the constant in the proof. In lean terms, this means going into the expression and changing every instance of, say, the 4 to a different meta variable. Then we abstract all facts about the constant in the proof. So in this same example, or in the square root of 17 example, once we've abstracted 17 to a meta variable, we also recognize that we have to abstract that 17 is a prime. So we abstract that proof that 17 is a prime into a meta variable. And then we detect other constants that depend on that abstracted constant. The way we do this is with the type check. So for example, in the sets of size 2 and 2 and 4, if we just turn the 4 into a meta variable but leave the 2's the same, then we'll end up with a proof that doesn't type check. And so we can recognize that there's a dependency there and recognize that what needs to be abstracted should be those 2's. And so then we abstract the 2's and abstract all facts about the 2's and so on until the proof type checks. And that's how we know there's no other dependencies. Okay, so then once we have turned all the relevant constants into different meta variables and all the facts or lemmas about those constants into meta variables, we can detect and unify related occurrences. So in the example of the sets of size 3, we recognize with the type check that this 3 has to be the same as this 3, and this 3 has to be the same as this 3, and unify those so that the meta variables that have to be the same are the same. The next step is we extract those meta variables as hypotheses. So For example, 17, the variable that used to be a 17 is now a universally quantified variable, and the lemma that used to be that 17 is prime is now that universally quantified variable, say n, must be prime. So those holes in the proof, those meta variables we created, become hypotheses that must be fed in for the generalized proof to work. And then finally, if we run type inference, we get the generalized statement. And so together, so then what we have is a generalized proof and via type inference, a generalized statement. Any questions there? Yeah?
May that loop forever? Because you have a loop there.
Yeah, so which, this one, if such a constant is found?
Mm-hmm.
I would think if the proof itself is finite length, I would think there could only be finitely many dependencies. I haven't, yeah. I can't think of a way to make that loop go on forever. Any other questions? Okay. And so far I've given some sort of shorter toy examples, but, well, actually I'll start with this. So I've given examples where you can generalize numbers, but I just want to make it clear that there's nothing specific about numbers. In this algorithm, we can generalize any constant. So for example, suppose we have this theorem that if we have 3 integers a, b, and c, and a plus b is a plus c, then we can cancel the a's and we get b equals c. We can generalize addition in that to an arbitrary binary operation. We can generalize 0 to an arbitrary, to an identity element that obeys certain conditions, that binary operation when it operates on that identity element, and some other element gives you back that element. And we can also generalize that type, the integers. And what we end up with is a statement that if you have an arbitrary type and a symbol representing the inverse, identity, and a binary operation, with the identity being left neutral and every element having a left inverse under that operation, and ensuring that the operation is associative and left cancellative, then you get cancellation. So this works for generalizing non-numerical constants as well, the same tactic. We can also look at a sort of bigger, longer example, a bigger proof. The proof, suppose we prove Bezout's identity in the integers. And again, this is like the way you'd expect to prove it. And suppose you prove, so just to state Bezout's identity, that if you have any 2 integers, x and y not equal to 0, then their integers h and k, such that their greatest common divisor g can be expressed as a linear combination hx plus ky equals g. We can generalize the integers z, and we don't, because of the way our proof works, you wouldn't expect to get that particular proof generalizes to an arbitrary Euclidean domain, but it does generalize, our algorithm finds that the same argument works in something close to an arbitrary Euclidean domain, as something close to being, using all of the facts that we used in the proof. So here you can see this at work, and I won't go into all of these, but all of these hypotheses that were extracted out, but you can see they make sense. You need the group to be additive, for multiplication and division to be defined on it, for associativity and commutativity to hold, so on. Okay, so some limitations. Proofs with black boxes can't be directly generalized. I want to emphasize that this is like proof generalization. So if any part of the proof is opaque, then it's not going to be possible to look into the proof and see what aspects about the constant you're trying to generalize were used in the proof. So we need all of those reasoning steps to be transparent for this to work. And so for that reason, if there are ever implicit uses of definitional equality in the proof, or for example, reliance on computation rules like reduce mul, that creates black boxes in the proof where we can no longer look at what was used about the constants to generalize. And that makes it difficult. This tactic, like those sort of things will not be generalizable with this tactic. Yes, question?
What exactly do you mean by a black box, though? Here?
Yeah. So this is my own terminology. I'm just trying to sort of anything where you can't see exactly what lemmas are being used.
But if you had
about
an
a
opaque,
constant.
if you actually had like an opaque proof, like someone had an axiom, which was that 17 is prime or something, that would be generalized here, right? It would just generalize it to an assumption that 17.
Yes, exactly. Yeah. So it would still work for those cases.
So that's not a black box in your definition.
Yeah, when I say black box, I mean where you can't tell what's being used about the constant. So in your case, you can tell, I guess 17 is prime. I forget what example. You can tell that that's what's being used. But if, say, that refers to another proof, or if in the proof that you refer to that 17 is prime actually uses something else about 17, but we don't have access to
But why
that.
wouldn't you have access?
If a computation rule was used,
So is this about like like these are limitations of the tool that you could overcome with more work?
so maybe I can. So here we have a proof that 2 times 3 is even, and you do it by unfolding even, and you find 2 times 3 can be written as r plus r, and then can be written as 3 plus 3. And now if you generalize the 3, then you know 2 times any number is even, and you can do this. But if the way that you prove 2 times 3 is even is by doing this calculation, and then this, and you try to generalize the 3, then we're not going to be, there's no 3 in the proof. That's obscured. And so we can't run this generalization tactic. So that's what I'm getting at with that. Yeah, thank you. Okay, so like, what's the use case of an algorithm like this? Well, I work in a group that works in human-oriented theorem proving, and this sort of proof generalization is something that we as mathematicians do all the time without even thinking about it. For example, if we have a conjecture and we end up disproving that conjecture with a counterexample, we'll very quickly try to figure out what the most general counterexample is. A counterexample is this set 1, 2, 3, and we find out actually, for example, it's a any 3-item set is a counterexample to whatever conjecture we made. And so we rarely think about this explicitly, but we're using this proof generalization process constantly. So any system that employs human-oriented theorem proving will have to be one that employs proof generalization. Yeah, that's all.